R was the brainchild of Ross Ihaka and Robert Gentleman, conceived in August 1993 at the University of Auckland, New Zealand. The main purpose for the R experiment was to come up with a better software environment in their Macintosh teaching lab that focused on statistical computation. During the early stages of development, a scheme-like interpreter was chosen as the best place to start. However, after considering the amount of changes and modifications they would have to make, they ditched the idea and decided to create their own from scratch. They still used documentation from the scheme interpreters as a template. The initial interpreter consisted of about 1,000 lines of code written in the language C. Data structures were added to support statistical work, and a user interface still had to be chosen. They ended up creating a command-driven interface that used S-like syntax. Some key differences between R and S is that R had memory management and scoping. Once the ball got rolling and R was functional for a minimal release, Ross and Robert made a small announcement in a publication called the S-News. Several people offered feedback on their code. The most feedback was given by Martin Mockler of the Swiss Federal Institute of Technology Zurich, or ETH Zurich. After about 2 years of development, Ross and Robert came to a point where they felt comfortable with their code. And given Martin's persuasiveness, R source code was finally released under the terms of the Free Software Foundation's GNU General License in June 1995. After this release, R gradually increased in popularity and began to surpass its original purpose as an environment for a lab in a university. By 1997, a core group was established to oversee and make changes to R's source code when necessary. This group is a loosely tied-together group that contributes feedback and code when they can with minimal interaction among its members. Today, R is still under active development. Its two main goals are to gain the ability to support moderate to large-sized datasets and to complete the introductory documentation for their language.
You can download R for free from their website. I'm going to open it here from the desktop. The console opens automatically. You can then also launch an editor. I like to cascade them vertically, work side by side, find it a little cleaner. On the console, you can easily bring up a demo menu, which then brings up a number of other options. Here, I'm going to ask for a demo on different graphics that R has built in. As you can see, it has a number of different standard charts it can display, which is pretty useful for statistical analysis. Commands can be entered either into the console or the editor. The commands compile on the console line by line and run when you hit enter. In the editor, you can run several lines or just a single line based on the cursor position, or by highlighting several lines at once and then hitting the Run Line button. Here we enter a number of values called a vector into the variable vec. By hitting the Run Line button, we save this variable and its values. We can then dump this vector into several methods. Here we find the mean, the variance, and standard deviation of our variable vec. Notice that as you hit the Run Line button, the cursor will automatically return to the next line of code. To see some of the more powerful features of R, we need to work with a database of information. We wrote a quick program to generate a CSV file, comma separated value file, which randomly assigns different values to a small database. Here we see what the file looks like when just open a notepad, all the bits of data separated by a comma. You can also load that into Excel. We can observe the data a little bit more cleanly. There are a number of ways to load this data into R. A quick shortcut is to just drop the file into the console. It then shows the file path, which you can copy and paste into the editor. We can save the entire database into a single variable. Here we're calling it SJU. The default setting for a header is true, so I don't need to specify it here. But if your CSV does not have header information, you need to set this to false. And now we just take a look at it by simply entering SJU into the console, and all 75 records here are now at our disposal. STR displays the database's structure, including all the headers, their data types, and examples of the data. Summary will display minimum, maximum, quartile, and average information on all of our data. The fix command, this is kind of neat, actually launches a data editor. Here you can go into any cell, easily change the information. Finally, we have the pairs command, which shows a matrix of correlation scatter plots, all with the headers being listed down the main diagonal. In the console, when you enter ls parentheses, it will list all the files and variables available to you. R comes preloaded with a few sample databases, such as this pedal length study that you can look at. In addition to the many packages that comes preloaded on R, you can download a huge number of additional packages from their website. This is open source, so it has a number of contributors. First, you just need to select a local mirror site. Then you simply search for the package you need and click OK to download. It's very simple. For instance, I want to create a decision tree. For this, I've already downloaded the party package, which recursively partitions data. We load the data we need from the pedal length study into a variable named iris_ctree. We're able to see the structure of the tree, but because we haven't loaded party into the console yet, the methods aren't going to work for us. Alright, now we've loaded the package and can call the method to print the tree. And now to plot the tree. The algorithm computes the highest information gain for each leaf node. For instance, if the pedal length is less than 1.9, it will always be the Setosa variety. So that's kind of like a quick rundown on a lot of the functions here.
Considering the presentation we just saw, we are now going to evaluate R on the 4 basic evaluation criteria: readability, writability, reliability, and cost. Judging from the previous presentation, the readability factor of R is very good. It is overall very simple with simple features and constructs. So orthogonal, it contains several different predefined data types, and R's syntax is relatively flexible. R is also a very easy language to start writing, therefore it scores high points for writability. As said before, R is simple and orthogonal, as well as being expressive in specifying operations. As far as reliability is concerned, there are several types of checks and exception handling one can perform in R. Readability and writability play a role in the reliability of the language, and judging from what was previously said, it scores high marks. And finally, there is the cost of R. Considering R is an open source language and free to use, cost is relatively non-existent. Overall, R scores pretty high marks in all categories. It has proven itself to be a useful tool whether you are playing around with some statistics or actually mining data.